Hello everybody. The next unit is called Mechanical Systems. That's the big name for it. Mechanical Systems. A mechanical system, in simple terms, is simply an object or objects, there could be more than one, and all of the forces that are acting on them. So in our previous unit, we learned a little bit about some individual forces. What we're going to do now is try to put everything together to describe an entire system, an object, all of the forces that act on it, and how that force eventually determines the motion of the object. So there's two sort of goals or things that we're trying to learn as we do this. The first is we're trying to figure out how to determine the net force on an object. We know a little bit about that already. And the second thing that we want to try to learn is to describe how that net force affects the object's motion. Affects the object's motion. Now, this can be thought of very simply or extremely complicated. It depends on the situation. So what we're going to do is start off with some nice, simple examples that will help us understand. So first, let's talk about the first thing, determining the net force on an object. So we'll make a little title here, and we'll call it net force. Net force. So what exactly is net force? Well, we kind of understand this already. The net force is simply the total of all the forces acting on an object. The word net is often used in accounting, and it kind of means the sum total, right? So the net force is the sum, we can use that word, because it reminds us that we are adding them up. The sum of all forces acting on an object. So that's pretty straightforward. All right, so we have to figure out how we're going to do that. Let's draw a picture just to kind of show us what we mean. Let's say, we have a tabletop or a road or any sort of, let's make it a table. And on this table, we have a large box. And the box might have a mass associated with it. So say the box is 10 kilograms. Well, what we need to do is we need to imagine the forces that might be acting on a box that's sitting on a table. The most obvious force is that there be a force of gravity pulling down. And so we can write Fg. Remember, Fg stands for the force of gravity. Now, if that was the only force, then this box should be accelerating down through the table and into the ground. But it doesn't do that. And that's because the gravity force is balanced or matched by another force, which is the table pushing up. The force of the table. We're going to learn that this is actually something that's called the normal force, but we'll get to that in a minute. So the force of the table is pushing back, and now you can see that these two forces are sort of balancing each other out. They're working against each other, and that's why the box is not moving anywhere. It's because the table force and the gravity force are kind of matched. So we would say that the net force is 0 at this point. But there could be other forces as well. Perhaps somebody is pulling or pushing the box. Usually when we draw pictures, we always draw it pulling, because pushing and pulling can be the same thing. And so we'll call this the applied force. And the applied force would be something trying to move the box. And then we have one more force that would try to stop the block from moving or try to oppose the motion of the block. And that is the force of friction. So little f means friction. You might want to write in the whole word for now until you remember what they mean. So friction and applied. Otherwise you may forget what these little words mean. Even this one, although we have done this one before, the force of gravity, there. We're going to use shortcuts as we go, but for now. So here's what we call a mechanical system. This entire thing is called a mechanical system. And mechanical system. It's an object and it's a bunch of forces that are acting on it. Now what might we want to do with this mechanical system? Well, some questions we might ask are, well, if I'm pushing the block, is it moving? We've all pushed things and made them move, so maybe this box will move if I push it. But maybe it won't. Maybe the box is so heavy that even if I push it with all my strength, I can't make it move. And so we like to ask ourselves questions like that. What will happen to this box on this table? And we would like to figure out whether or not the box is going to move, and if it does move, how will it move? Will it accelerate? Will it get faster and faster and faster? Will it move at a constant speed and just kind of slide along? And these are all the questions that we want to figure out. So, in order to do that, we have to first notice something very important about this picture. There are basically two sets of forces. If you look at the picture, you will see that there are arrows that go up and down, like the table, force of the table, the force of gravity. And there are arrows that go left and right, like the force applied. Maybe, hang on, I'll do that in different colors so that we color code everything here. So let's see, we have forces that go left and right, like the applied force and the friction force. So one of the things we like to do in physics is we like to break it up to make it simpler. We break it up and we look at the up and down forces separate and the left and right forces separate. And the reason we can do that is because moving up and down has no effect on moving left and right, doesn't it? You can't go higher by moving to the side. And so because the two have no effect on each other, there's no reason why they have to stay together. We can look at them separately. If you recall when you were a kid, you might have played on the Etch-a-Sketch, right? Which is a screen, and on the screen you could draw pictures by turning two knobs. One of these knobs, if you turned it, moved the drawing device left and right, and the other moved it up and down. So I'll color this one green. If you spin the green knob, then the picture on the screen would move back and forth. But that's all it would do. No matter how much you turn that knob, it would never go up or down. And of course, if you turn the red knob here, I'll color this one red for up and down. When you turn this knob, the little drawing device would only move up and down. You could turn that knob all day, but you would never ever get the drawing to move to the right or the left. To get something going up and down and left and right, you would have to turn both knobs together. And then you could go over and up and down, and you could make any kind of drawing on the Etch-a-Sketch that you wanted. But this would require turning both knobs. So you can see how the sideways motion has no effect on the up and down motion. And that's true for not just the Etch-a-Sketch, but it's true for real life. So we have words, of course, right? We have sideways motion. Sideways is the word that you might use. Sideways, we use the word horizontal. So the word horizontal refers to motion that is sideways, back and forth. And of course, the other kind of motion is what we would call up and down motion. Up and down motion, we call it vertical. So the word vertical refers to motion that is up and down. And so what we're going to do is we're going to look at our picture again of the box on a table. And we are going to only look at either up and down arrows or left and right, but never all four together. We're going to keep them separate. All right? Now, if you recall your math class, you've often seen a graph that was drawn, and the graph has these two lines on it. This line is horizontal, and this line is vertical. As a shortcut, instead of saying the words horizontal and vertical all the time, because they're big words, we gave them nice handy letters, X and Y. So when we talk about X, we're talking about sideways, horizontal things. And when we talk about Y, we are talking about vertical things, up and down. Okay? So, let's go back to our picture. And let's color code it slightly differently. Let's draw our picture again. There's our table. And here's our box. And I think the box was 10 kilograms. In the blue, I'm going to draw only the up and down vertical forces. So here we have the force of the table. And the other one was the force of gravity. Now, to describe these two forces, I'm going to use an equation or a mathematical sentence. What I'm going to say in English is that the total force, actually the total vertical force, up and downy force, the total vertical force is the sum of, right, the adding together of the force of the table and the force of gravity. You have to add those two together to figure out what the total vertical force would be. So, and the force of gravity. Now that's a big sentence. It's a lot of words. So what I'm going to do is I'm going to use our good friend mathematics to rewrite this. Total force is what we call net force. Remember, the word net means total. So I'll take this part right here, the total vertical force, and I'll replace it with the F net. And then it said is. Well, in math, for is, we use equals, right? It's equal to. Now, the next part is the sum of the force of the table and the force of gravity. So for shortcut, I'll write the force of the table plus the force of gravity. And if we don't write all of the words in, we often like to take shortcuts. F net equals F. We could put a little T for table and a G for gravity. So you see how we get shortcuts. And that's how we would describe the vertical forces of that particular picture. Now, we weren't looking at the other forces. I'll put them in the picture so we remember they're here, but I'll dot them so we don't focus on them. Remember, this was the applied force, and this was the friction force. Force of friction, force applied. But we're not looking at those right now because they are horizontal. They are not vertical. So they're still there, but we're just letting our eyes focus up and down. Now we have to talk about something a little bit not complicated, but just one extra thing to throw into the mix. You see this table pushing up? It's the force of the table, right? Well, what if it wasn't a table? What if, let me draw a couple of, okay, I'll tell you what I'll do. I'll give you a title, because this is what we're going to eventually call this. It's actually called the normal force, this force of the table. And the reason we give it a special name is because it's not always a table. It could be anything. So for instance, if you have a car sitting on the ground, right? Well, the car sitting on the ground has the force of gravity pulling it down. But the ground pushes back up. And so the force of the ground is called the normal force. Now, if you remember math, and you may have heard that the word normal in math, it doesn't mean that you're like, abnormal or psychotic or crazy. The word normal means perpendicular. And if you look at this force right here that I've drawn, you can see that it's perpendicular, which means at 90 degrees to the ground. So that's why we use the word normal. It means a force that is perpendicular to a surface. So the first thing we learn about the normal force is the normal force is perpendicular to the surface. In other words, you need a surface to have a normal force. Always perpendicular, that means 90 degrees, right? Maybe you can put that, if you forget what the word perpendicular means, put 90 degrees to the surface. Now, the surface could be a table, like in the first example. It could be a car on the ground. It could be anything. It could be, let's see, it could be a desk. It could be a skating rink, right? A curling stone. If you like to curl, you hurl the stone down the ice, and this is the stone. And of course, the gravity pulls down on the stone, but the ice also must push up. Because if it didn't, whoops, that's the normal. If the ice didn't push up, then Newton's law tells us that the gravity should pull this stone right down to the center of the earth. And it doesn't do that because the ice is in the way. So the ice is pushing up. So that's called the normal force, right? Now, in the examples we are going to do, we're going to keep our normal force always pointing up until we get the hang of it. But it is possible for the normal force to point in other directions. But we won't worry about that. That's sort of later, once we become really, really good at dealing with the normal force. So if we go back to our little equation that we wrote right here, instead of the force of the table, what we could write instead is just the normal force, which means whatever it is in the question. It doesn't have to be a table, it could be the ground. So our new equation would be F net now equals the force of the normal, right? The normal force, which would be the table pushing up, plus the force of gravity. So you see how we turned it into this. One more thing I'm going to add, because we're talking about the up and down forces only, remember, we're talking about the vertical forces, which on the graph are the y-axis. I'm going to put a tiny y right here to remind me that this equation is all about up and down. And so this represents what I wrote in words up here in blue. Let's go back and look what it said in words one more time. It said that the total vertical force, right here, is the sum of the forces of the table and the force of gravity. So we're calling the force of the table the normal force. It's the force of the surface pushing up. And we're calling the force of gravity Fg. So we go down here and we say in math language, the total vertical net force, the total up and downy force, is equal to the normal force, which is the surface pushing up, and the force of gravity. Now, we can actually put numbers into this and find out some valuable information. Let's look at that again. Once again, I will draw the picture. Right? Now, when you're doing this, you can draw one picture because you can see it. But because we have to move our board, our picture keeps disappearing. So let me just draw the picture again so you can see it. Here is the 10 kilogram box on the table. And here is the force of the table pushing up, which we call the normal force. And here is the force of gravity pushing down. Let's write our little expression that describes the overall force, the total net force in the up and down, or y direction, is equal to the force of the normal plus the force of gravity. Now, let's figure out what we can do with this. And to do that, over here on the side, we're going to remind ourselves of two things we learned in the last unit. We learned that the net force on an object causes it to accelerate. F net equals ma. That was Newton's second law. So we have this little bit of information available. The other thing we learned in our last unit is that the force of gravity is equal to the mass of an object times gravity's acceleration, little g. These two equations should look familiar to you. So when I write my expression over here, this is kind of like writing an essay. I'm going to change some things as I go. The net force, which I wrote right here, is equal to ma. And so I'm going to write in its place ma, because they're the same thing. That's what Newton's second law tells us. The normal force is just the same as always. But the gravity force is, if you look here, the force of gravity is mg. So I can replace this with mg. Okay, so the first thing we do is replace whatever we can with simpler expressions that they represent. So you see how we used Newton's first law to turn that into that, sorry, Newton's second law, and we use this to turn the force of gravity into that. Now we have another problem. We're trying to write this little story in mathematical language, but mathematics cannot see our picture. The numbers don't know what we're looking at. We can see it, and the first thing we notice is, well, look at this force of gravity right here. Oh, it's going down. See, there's the arrow pointing down, and the normal force right here is pointing up. We can see it, but the mathematics cannot. So we have to tell the math. We have to tell in our story which way these arrows are pointing. And an easy way to do that is to use negative signs for any arrows that point down and positive signs for any arrows that point up in our math. Let's see if we can add some numbers into our equation, and let's think about which way the arrows are pointing. ma is the first thing we have right here. Well, if you look here, the mass of the object is 10 kilograms. So I can put a 10 where the m is. That leaves me with just an a. I don't know anything about a, so if you don't know anything about it, you just leave it as it is. I also don't know very much about this normal force. I know it's there, but I don't know any numbers that go with it. But I also know about the mass right here of the object. It's also 10, and I know the 9.8. So you see how I can put those numbers in. But gravity, the arrow, is pointing down, right here. So in order to tell the math that it's pointing down, I have to change this to a minus. Minus means down. So you see how the normal force looks positive, so it's up, and the negative means down. So that's the next step. It's very important to remember to use pluses and minuses for your ups and downs. Now, let's try to do something with this. Well, one of the easiest things we can do is on this end, we can multiply 10 times 9.8. That's easy. That's 98. Fn we really can't do much with at all. Now what does A stand for? A stands for acceleration, right? Acceleration. Let's go back to our picture and look at something interesting. Here's our picture. And don't forget, we also had somebody pulling, but we didn't want to put that in because we were only looking at the up and down forces, right? I'll get rid of this arrow. And we had a friction force, but we're not looking at those right now. They're sideways, and this is all, here's my little y, right? These are all up and down vertical forces. Let's imagine what would happen if you had a book on the table, and even if you did push it, would the book go up? Probably not. If you pushed it, it would go sideways. If you pulled it, it would go sideways. The book is not going to move upwards in any way, and it's not likely going to move downwards through the table either. The table is probably strong enough to keep the book up. So if there's any kind of motion at all, this book will move sideways, but it will never move up or down. We wouldn't expect it to just suddenly fly up off the table. or pull itself down under the table. It's only going to move back and forth. So that means that there is no vertical motion. Okay? So, if there is no vertical motion, what does that tell us about the kind of acceleration we would get up and down? Well, it tells us that the up and down acceleration, I'll put a little y beside it, must be 0. There can't be any acceleration up and down. Now remember, we are only looking at up and down. So that means that the little a here will have to be a 0, because there's no way this book is going to move up or down. And it's certainly not going to accelerate up or down. So look what happens to our little story that we're telling. 0 times 10 is 0, Fn minus 98. Well, you know the rules of math. We can move the 98 over to the other side of the equation by adding 98 to both sides. And so what it turns into is positive 98 equals Fn. And since we're pretty much done here, we've reached the end of our story, we'll add in that this is a force, and we'll add in the unit of newtons to remind us that it's 98 newtons. Notice how the number turned into a positive right here. What does that mean? Well, it means that the normal force is up. And sure enough, on our picture, that's exactly what we expected. The normal force is up. There it is, the arrow's pointing up. So by telling the math about the gravity being down, right here, when we said, hey math, see that? That's a down force. The math was then able to pick the correct direction for the normal force, which is up. That's why that's so important. So what have we figured out? Well, we figured out that basically this is the amount of gravity right here, and this is the normal force right here. We figured out that the normal force is equal to the gravity force, but opposite direction. All right? One is up and one is down. That's a lot of work to do something that was pretty obvious from the picture, isn't it? If you look at the picture, yeah, sure, one is up, one is down. If it's not moving, it makes sense that they balance each other out, so they're the same. But this little story that we wrote right here and all the way down, this little story is how we would say that very same thing using mathematics. And it's important to learn how to use mathematics to tell your stories in physics, because as you go on, the stories will get more complex. It'll be too hard to tell them in English. So, what I'm going to do is give you a couple of questions to practice with. So you have an example there to follow. I'm going to do a couple of practice questions. Here is the ground, here is a box, and on this box I'm going to write the mass of 20 kilograms. All right? And your job is to find out what the normal force would be. That's what we're trying to figure out. I'll give you another example. Here is a car sitting on the ground, and the mass of the car, I'll just write it over here so it doesn't get, is 800 kilograms. It's a big car. That's more like a truck. 800 kilograms. Find the normal force, which would be the force of the ground pushing up. And I'll give you one more example. And I will say, okay, let's do you on your bicycle. So here's your bicycle, right? And you're riding your bike. Here you are. Da, 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 da. Put your feet on the pedals. Okay, that's a pretty sad bike. But the mass of you and the bike is 100 kilograms. Heavy bike. And so your job is to do the following things. All right? Here's what I want you to do with these three examples. The first thing I want you to do is draw the diagram, the free body diagram with all the forces on it. Now, so far, we are just looking at up and down forces, so we're not doing any lefty-righty things. Draw the free body diagram, and let's just draw the vertical up and down forces only. Okay? Then, I would like you to write the net force equation, which is that sentence. Write the net force equation. And I'll just show you, in case you're not sure what that means. That's what we started with, back up here. Oh, we have a whole extra page there. Way up at the back, way over here, way back here. And I'm running out of colors, it's getting kind of complicated, but this is the net force equation, right? Showing that it basically says the total vertical forces equal the sum of the normal force and the gravity force. So that's what you would write next. That's going to be the same for every picture, for the ones that we do anyway. Now let's go back down. And the third thing I would like you to do is use that equation that you've written, all right? Put in the numbers that you can, whatever numbers you can think of. The masses, 9.8, and so on. And find the normal force. Do those three things for all three pictures that we drew right here. So now pause the video and try and do all three on your own. And then when you're finished, or if you get stuck, come back and I'm going to now show you the solutions. But don't just watch the answers. Please stop the video and try to do it on your own first. Okay? All right, so now you're back. You've tried all three. You've done your homework. Let's do the first one. The first one was a block, and it was sitting on the ground. And I have to go back and check because I forgot the mass of that object. I thought it was 20 kilograms. There it is. So 20 kilograms. So we're going to put 20 kilograms in the box to show its mass. Right? 20 kilograms. So the first part said draw the free body diagram with the forces. Well, you know that this box has a force of gravity that's trying to pull it down. That's also called the weight of the box. And you know that it has a force from the surface, the ground or the table or whatever it's on, that pushes up, called the normal force. So there's the free body diagram showing only the up and down vertical forces, because that's all we're talking about right now. Now we draw the net force equation, which says that the total forces, or the net force, in the up and down vertical direction, that's what Y stands for, is equal to, well, let's look at the picture. There's two arrows, up and down. There's a normal force, and there's a gravity force. So that's step 2. Perfect. Step 3, then, is to put in whatever numbers we can think of that will make this work. So the first thing we do is we say Newton's law says that net force equals ma. So we change this to ma. Remember, that's from this equation. I'll write it again so you remember where it's from. Newton's second law. Fn. And then over here I'm changing the gravity to mg, because another thing we learned was that the force of gravity is equal to mg, so we can make those changes. Now I'm going to put in the masses of 20 kilograms here, but guess what we said before? This block is not going to accelerate up or down. There will be no vertical motion. So the acceleration is 0. And that leaves me with the normal force. And then I have a downward force that is 20, the mass, times 9.8. But because it's down, I'm going to put in this negative sign to show the math is pointing down. Critical part of the problem. If you get that wrong, everything else will be a mess. So now 0, 20 times 0, and then over here, 20 times 9.8 is 196 minus. And then, of course, we move that to the other side. It becomes positive 196. I'll remind myself that we're talking about newtons, and there's the, don't confuse the normal n with newtons, two different n's, right? So 196 newtons is the normal force. That's how hard the table is pushing back up. And of course, the table is pushing up. So you know what? We could write here, the table or the ground, whatever that is, pushes up with 196 newtons. And of course, the interesting thing is, what that means, it's a force. That force is equal, oops, I better write that in better English. A force that is equal to the weight of the object. It's supporting the weight. The object's weight. And that's exactly what tables and ground does, right? It supports the weight of the object and keeps it from falling. Very interesting. Okay, let's look at example number 2, which I believe was an 800 kilogram car. There it is, 800 kilogram car. So let's go down here and let's do all the way down. Good. 800 kilogram car. All right, I'm having some trouble getting this to move. Maybe I've reached the limit, I don't know. 100 kilogram car. So we have a car, and here it is. There's the car, 100 kilograms. I'll put over here m equals 100 kilograms. It's too small to write on the car. So guess what we do? Well, the force of gravity is pulling down on the car. The ground is pushing up, which is the normal force. So there's my diagram. Then I write that the net forces up and down, vertical, are obviously equal to two things, the normal force and the gravity force. And it doesn't matter which order you put these in. If you want to write Fg first, in fact, watch, we'll do it, it won't make a difference, just in case. All you have to do is add them up. So adding 4 plus 2 is the same as 2 plus 4, so we can write Fg first if we want. So watch what happens if we do that. Now, we look at this and we say, okay, what can I do? Well, for some reason I'm stuck and I can't go down. Okay, I had to erase my page there so I could start over. Unfortunately, I ran out of room somehow. So let's go back to our car. There it is. It's a terrible car, but a mass of 800 kilograms. Okay, so what we had done already was we drew the normal force pointing up and the gravity force pointing down, and we had written that the net force in the up and down direction is equal to, this time we put gravity first and then the normal. Okay, now F net, remember, equals MA. It always does, no matter what. So we put MA here, that's Newton's law. Fg is equal to mg, right? We already knew that. And the normal force. Now the mass of the car is 800 kilograms. But is the car going to have any up and down motion? No. So there's no acceleration. 800 kilograms times 9.8 goes here, but now that I'm putting numbers in, I also have to remember the force of gravity is pointing down, so I have to put a minus in front of it. Notice I don't put the minus over here because that would make the normal force minus. So the sign, the plus or the minus, always goes in front for up or down. Okay? Always goes in front. And that leaves me with plus Fn over here. And so we have 0 equals, okay? Now if you multiply this, 8 times 8 is 64. And 9 times 8 is 72. It's 784. And of course we're going to multiply, I think, by that. We have one decimal place. So I think it comes out to about that. 7840. And minus, because of the minus sign, which is basically telling us that it's down. And we move it to the other side, and the same thing happens. 7840 newtons is the normal force. Excellent. And that's the answer to that. And we do it one more time for our 100 kilogram bicycle. So here you are on your bicycle. Okay, and that's you. And your mass is 100 kilograms. And so what do? We draw in the forces. There's gravity pulling down. And there is a force of the ground pushing up, which is what we call the normal force. The total force in the up and down direction, F net y, is equal to the normal force and the gravity force added together, the total. Newton's law tells us that F net always equals ma, and Fg is the same as mg. That's how we calculate gravity. The mass is 100 kilograms. The bicycle will not have any up and down motion, so the acceleration is 0. And the normal force stays the same, and this time we put minus for down, and 100 for the mass, and 9.8 for gravity. So you see how the minus sign is for down. 0 equals Fn minus 980. And that means, if you move it to the other side, that the weight of this object, remember, force of gravity is equal to the weight. So the weight of the object is 980 newtons. And so the normal force has to support the weight, so the ground pushes up with 980 newtons upwards. And that's how you calculate the normal force. It's also how we describe the uppy-downy forces on an object. In the next video, we'll talk about the lefty-righty forces, or the horizontal forces on the same objects.